Welcome to the introduction to implicit differentiation. So implicit differentiation allows us to find derivatives of functions that are not defined or written explicitly as a function of a single variable. Right? So for instance, what that means is we can't write the function explicitly in terms of y, right? Where we have y isolated. And here's an example. X squared plus y squared equals 25. Right? So let's try to solve for y. Right? So first we would subtract x squared from both sides. That would give us y squared equals negative x squared plus 25. And then we want to solve for y. We have to take square root of both sides. Right? And if you're solving for something squared, don't forget you've got to take plus or minus. Right? So when you're solving a quadratic, for instance, by taking a square root, you have to take the positive and negative square root. So here we also have to take the positive and negative square root. And so that gives us y equals plus or minus the square root of negative x squared plus 25. We've got two solutions. We've got a positive, we got a negative. Do I use the positive or the negative answer? There's no way to solve for y. So here's an example of a function that we can't explicitly solve for y. And using the tools you have right now, you would have no way to take the derivative of this function. But we're going to learn a new tool. And that's going to allow you to take the derivatives of these functions. All right, so let's just look a little bit more, though, at implicitly defined functions. Right? So it's called implicitly defined because we can't explicitly solve for a single variable. So an important problem in calculus is how to find the slope when the function can't conveniently be solved for y. Instead, y is treated as a differentiable function of x, and both sides of the equation are differentiated with respect to x, using the appropriate rules for sums, products, quotients, and the chain rule. In other words, the rules you've already learned. There's just one little addition, and that is that we've got y stuck in our equation. And so whenever we see a y, we're going to have a chain rule, and we're going to take the derivative with y with respect to x. And the derivative of y with respect to x is dy dx. Right? So that will and then we just have to solve for dy dx, because dy dx is the derivative, and then we'll have a formula that calculates the slope at any point xy on the graph. The process by which we find dy dx is called implicit differentiation. The phrase derives from the fact that the equation, so here's an example, x cubed plus y cubed minus 9xy equals 0, right, defines functions implicitly. Right? We've got an x cubed, we've got a y cubed, we've got a 9xy, and there's no way to separate a single variable here. Right? And so because our variables are stuck together and can't be isolated, we can use implicit differentiation to solve for our derivative, right, to find the derivative, because there's no way to rewrite that function explicitly in terms of a single variable. Here's, by the way, what that function looks like, and you might notice something about implicitly defined functions is that they're really not functions at all, are they? I mean, this clearly does not pass the vertical line test. You can see that we've got three values of y given a value of x. So you can see why there's no way to solve for the dependent variable y. Right? Just absolutely no way. But fortunately, we don't need to. This is in your notes. This is the steps for implicitly differentiating. So to find dy dx, we're going to differentiate both sides of the equation with respect to x. In other words, we're not going to move a darn thing. We're just going to take the derivative of all the different terms, treating y as a differentiable function of x and applying the chain rule. So whenever, by the way, add the red writing to your notes. When we take the derivative of y, it's always going to be a chain rule, and it's going to include dy dx. Oh, that's an awful looking parentheses. Let me see if I can make that look a little nicer. Dy dx. Right, so our first step is to differentiate both sides of the equation with respect to x. We're going to collect the terms with dy dx's on one side of the equation, and everybody else goes to the other side of the equation. We'll factor out dy dx and then solve for dy dx. In other words, isolate it. And then you've got your derivative because dy dx is the derivative. Here is the equation we started with. And we're going to not only take the derivative, we are going to find the slope of the tangent line. And that thing says the. When x equals 3, what is the slope of the tangent line? And I actually had to pick I decided to pick one of the points, because when x is 3, y is either 4 or negative 4. Take your pick. I have that solved below. Matter of fact, everything in here is in your notes except for two things. This first thing over here, 3 squared plus y squared equals 25, right? Because x is 3. That would give us 9 plus y squared is 25. Subtract 9 from both sides. You got y squared is 16. But when you take the square root, there's two solutions, right? Positive and negative. And if you think of this particular equation, I'm just going to quickly just sketch it to remind you what this looks like. You don't need to do the sketch. So this is the equation of a circle. It has that was supposed to be at the origin, has the center at the origin, and then 1, 2, 3, 4, 5. Oh, so close. 1, 2, 3, 4, 5. It has a radius of 5. Right, so this is actually what it looks like. Well, somewhat. Pretend that's what it looks like if this were circular. There we go. And so if we look where 3 is, notice we've got two different points there. We've got this point here, 3, 4, and we've got this point here, 3, negative 4. So I just decided to choose one of those, 3, 4, just for our very first problem. And actually, you might want to include that in your notes. I'm just going to move that off to the side. And that might remind you why there's two solutions here for what's y when x is 3. But I just decided we'll just take 3, 4. I can make those executive decisions. All right, so our first step is to differentiate both sides with respect to x. The derivative of x squared, that's just the power rule. Exponent moves in front, and we reduce the power by 1. Plus, now the derivative of y squared is almost the same thing. We can use the power rule, except it's a chain rule, right? Because we're not taking the derivative with respect to y, we're taking the derivative with respect to x. So every time we take the derivative of y, we need to do a little chain rule, right? So the derivative of blop squared is 2 blop. The derivative of the blop, the derivative of y, is dy dx, right? So technically, this is just a little chain rule here. Right? And so you can just think of it as the derivative of blop squared, 2 blop. And then the derivative of y with respect to x is dy dx. Now you might wonder, why don't we take the derivative of x with respect to x? Well, the derivative of x with respect to x, you might want to put that in your notes so you never ask this question again, is dx dx, which is just 1. Right? Anything divided by itself, with the exception of 0 divided by 0, which we know is undefined or indeterminate, would be 1. Right? So we don't bother to write it down because it'd be just like multiplying by 1. So we have 2x plus 2y dy dx equals, and the derivative of a constant is 0. Right? So we're almost done. Now we need to gather up the terms with dy dx on one side and the terms without dy dx on the other side. So we'll subtract 2x from both sides. So we have 2y dy dx equals negative 2x. We just subtract 2x from both sides. And now we want to solve for dy dx, which means we will divide both sides by 2y. And that gives us dy dx equals negative x over y, because we'll reduce those 2's, right? So we divide both sides by 2y, we'd have dy dx equals negative 2x over 2y, but there's no reason you can't just reduce and get negative x over y. Okay? And so now we wanted to find the slope when x is 3, and I have two different choices there. Actually, we could find them both. It's really not that difficult. So here is when it is, and so I'll write down 3, 4, and 3, negative 4. And you can see we'll have two different slopes. And as we should, because, well, notice the tangent line at 3, 4 is negative, and the tangent line at 3, negative 4 is positive. Right? So for 3, 4, our slope would be dy dx equals negative 3 over 4. The slope is negative. For 3, negative 4, the slope would be negative 3 over negative 4, and that would be positive 3/4. Right? Now, if you're told the x and y value, you're told just to find the slope of the tangent line at 3, 4, then you would find a single answer. If we're told just to find it at x equals 3, technically you'd find both of them because there's actually two tangent lines at x equals 3. Right? So just be careful on that part. There may be more than one answer because there may be more than one tangent line at any given point. Right? Because this, you can see, is not a function that is isolated for y. This isn't even a function at all. Right? The circle does not pass the vertical line test. All right, so that's our first one. And basically these are the steps. Now we're going to add in a few more rules like chain rule. Well, we have a chain rule no matter what with the y, but we'll add in a chain within the chain. And then we'll add in product and quotient and all of our other rules as well, and trig functions, and we'll find the derivatives of all kinds of functions. Like this one. Right? So here we have 3y squared plus 2y equals 5x. Tell you the truth, this one's not that much harder. It's not really any harder than the one we just did. So we'll take the derivative of both sides, right? And of course, anytime we see a y, that's going to be a chain rule. So the derivative of 3y squared is going to be, this is just going to be a power rule, right? With a little chain, right? So this would be 3 times, so this is just blop squared, which is 2 blop. Right, so 3 times 2, actually let's use parentheses, and the exponent reduces by 1, and then it's a y, so we have to have dy dx. Right? So the chain rule part is the derivative of y with respect to x is dy dx. Plus the derivative of 2 blop is just 2, and then we have to take the derivative of the blop. The derivative of y with respect to x is dy dx. The derivative of 5x is 5. All right, so let's just simplify that a little bit. That's just 6y, and you didn't have to do that as 2 steps. I just want to make sure you saw that you had to multiply 3 times 2. So we have 6y dy dx plus 2 dy dx, whoops, lost my d, 2 dy dx equals 5. We already have all the terms with dy dx's on one side. That's why it says move all the terms without a dy dx, done. Right? It's already, the term without the dy dx is already on the other side of the equation. We'll factor out dy dx. That just means we're going to divide both of those terms by dy dx. So we divide, if we factor out the dy dx, we'd be left with 6y plus 2 equals 5. And now divide both sides by 6y plus 2 to isolate dy dx. And that's all there is to it. So dy dx equals 5 divided by 6y plus 2. And we're done. Right? A lot of times your derivatives may end up with x's and y's in them. That's okay. This one only has a y. On to the next one. And I tried to give you a little hint if it was in your notes by putting the word notes above it. Lenses, tangents, and normal lines. In the law that describes how light changes direction as it enters a lens, the important angles are the angles a light makes with the line perpendicular to the surface of the lens at the point of entry. And I have a picture on the next slide. This line is called the normal to the surface at the point of entry. In a profile view of a lens, the normal is a line perpendicular to the tangent to the profile curve at the point of entry. And a picture is worth 1,000 words here, and I'll show you that in just a second. Implicit differentiation is often used to find tangents and normals of lenses described as quadratic curves. So remember, a normal line is a line perpendicular to the tangent line. Right? And as a reminder, slope is a negative reciprocal and it goes through the same point. Right? So if you're not sure about what a normal line is, write that down in your notes. Right? And by the way, you can just pause this tape at any time if I go too quickly. That is one nice thing about taping. So here's my picture. Right? So the green there is the curve of the lens surface. You can think of lenses on a microscope or a telescope or glasses, right? Or your eyeball, right? And then the light enters. So the tangent line is the line that it's perpendicular, right, to that point of entry. It just touches at one point, and then the normal line is perpendicular to the tangent line, right? So they create right angles, right? And so often we're interested in that normal line that's perpendicular to the tangent to the curve. And we can find that, right, by just finding the slope of the normal line, which is just the same slope but negative reciprocal. All right, so here is the equation for that lens. Right, so x to the fourth plus x squared y squared minus y squared equals 0. At the point, square root of 2, 2, square root of 2, 2. Right, so here this was going to involve a product rule and a chain rule, right, because x squared y squared is a product. And because there's a y, it's a chain. And here we're given a specific point, right? So we're not going to have two different points like we did in the last problem. We are given the point to use. And all the writing on the side, that's just 4x cubed. Derivative of x squared y squared, right? So now that one's going to be a little product rule. Or not a little product rule, it's going to be a product rule. You know what, let's just write that, maybe I'll write that off to the side over here just to remind you. All right, so we have a product. Let me write that nicer. Just to remind you of product rule. If we have a product, UV, that derivative is going to be the first times the derivative of the second plus the second times the derivative of the first. So in this case, the first is x squared, and the derivative of x squared is 2x. The second term, the v here, is y squared, and its derivative is 2y dy dx, right? We need that chain part of it. Right? So our derivative is going to be 4x cubed plus the x squared times the derivative of y squared, which is 2y dy dx, plus the second, which is y squared, times the derivative of the first, which is, and so if you like to write the x's first, you can write 2x. If you want to write the y squared first, we can. There's the second. And the derivative of the x squared, of course, is the 2x. And then we need to take the derivative of y squared, which is going to be minus 2y dy dx. Now, if you're wondering, well, why you can't read that, it's because the board stinks. If you're wondering, next to the y squared, and it's because, oops, come on, no. We didn't take the derivative of y squared, it was the second. Oh, my goodness. Can we just move that a tad? Come on. There we go. Oops. Good little board. Okay, good enough. I think you can read the dy dx over there. All right, so now we need to isolate things that have dy dx's on one side. Oops, equals 0. Sorry. Got to take the derivative of 0, which is 0. All right, so we've got two terms with a dy dx and two terms without. Let's move the terms without the dy dx to the other side. So, and then let's clean up these terms, because normally we wouldn't have x squared 2y. We'd put the coefficient first. So 2x squared y dy dx minus 2y dy dx equals, and then we'll subtract the other two. So that would be equals a negative 4x cubed, and then minus, we'll change the order there to be 2xy squared. I kind of like to put the x's first. Alphabetical order. We will factor out dy dx. So if we factor out the dy dx, we're left with 2x squared y minus 2y. Right? Just factored that term out. Equals negative 4x cubed minus 2xy squared. Boy, there's not a lot of space there. And then we'll divide both sides by 2x squared y minus 2y. To isolate dy dx. I could really use some kind of border here between the first part that I wrote and the second part. So dy dx equals negative 4x cubed minus 2x y squared divided by 2x squared minus 2y. And if you notice, every single term is divisible by 2. Let me see if I can, if you're trying to read this and you're getting lost in the sea of green, there we go. There's the first part. There's where we were taking the derivative. If you notice, everything is divisible by 2, so let's divide by 2. This should be in reduced form. So dy dx equals negative 2x cubed minus xy squared divided by x squared minus y. And we are done. Oh, no, we're not done, because we need to find the equations of the tangent and normal lines at that particular point. All right, so we found the derivative, and that's all we've done. Now let's do the rest. And I think I saved myself some space on the next page because I have no room on this page. I did. And I think that's the same derivative, hopefully, that we got over here. Negative 2x cubed minus xy squared, x squared minus y. Wait, we have an extra y, don't we? Did I lose somebody? Oh, I lost somebody. I did indeed lose somebody. Sorry. When I was writing it down, we just lost the little y there. Well, it's a good thing I already, had it written down. Just completely lost the y. I guess I got lost in the sea of green. Was more interested in putting a black line around and somehow lost my y. But it's okay because we have the y back. Oops, wait. Except, oops, we reduced. So it should be negative 2x cubed minus xy squared all over x squared y minus y. Okay. And that is what we have on this page. All right, so now let's plug in. All right, so if we want to find the slope at a specific point, we have to plug in the point, right, into our slope. So dy dx evaluated at square root of 2 over 2, square root of 2 over 2, that's a point on the curve. Right? And to find the slope, we just plug that point in. So everywhere we see an x, well, actually, anywhere we see an x or a y, since they're the exact same number, we're going to plug in a square root of 2 over 2. So we have negative 2 times the square root of 2 over 2 cubed minus the square root of 2 over 2 times the square root of 2 over 2 squared divided by square root of 2 over 2 squared times the square root of 2 over 2 minus the square root of 2 over 2. All right, and then let's simplify that. Let's see. Do I have enough space over here? Maybe. All right, so we've got negative 2 times. All right, so square root of 2 cubed is be the square root of 8, which we'll simplify afterwards. And then 2 cubed is 8 minus, all right, so the square root of 2 squared is just going to be 2, right? The square and square root cancel. And then times the square root of 2 is going to give us 2 square roots of 2. Everyone okay with that? Right? So, and actually if it helps, you know what? I won't combine two things at once. I'll just leave the square root of 2 over 2. And then I'll just do the squaring. And then we'll simplify. Because we have to simplify the other term anyway. So the square root of 2 squared is going to be 2. And I don't think I remember to square root the 2 anyway, over 4. Right? And then square root of 2 over 2 squared is going to be 2 over 4 times the square root of 2 over 2 minus the square root of 2 over 2. All right, now let's simplify that. The square root of 8 is 2 square roots of 2, right? It's 8 is, you don't need to write this down, right? 4 and 2 and 2 and 2. And 1, 2 comes out and 1, 2 goes away and 1, 2 stays under the radical, right? So that's going to be negative 2 times 2 square roots of 2 all over 8 minus and 2. Well, we should probably reduce, right? So that's a 4. And actually, that's a 2. So now we've got the square root of 2 over 2, negative square root of 2 over 2, minus we've got a lot of reducing over here. We had square root of 2. This was we had a square root of 2 times 2. So that's going to be minus 2 square roots of 2 all over 8. Right? But we could reduce that to a 4. And actually, we got to subtract these terms, and they need a like denominator. Maybe we shouldn't reduce quite so much, because I can't do anything else with that other term. So let's just keep this as square root of, or 2 square roots of 2 all over 4, and just reduce. Actually, let me write that as 8. There, then you can see what we did. So let's just cancel out one of the 2, so we still have the same denominator. All over, and then now I can do a little bit of reducing there. So that would be 1/2 times the square root of 2 over 2. Well, that's just going to be the square root of 2 over 4. Right? Square root of 2 over 4, because this is just 1/2, minus the square. Now I'm going to have to make that 2 square roots of 2 over 4, otherwise I'm not going to be able to subtract. Equals, so we've got 2 square roots of 2 over 4 minus the square root of 2 over 4. That's a square root of 2 over 4. Divided by square root of 2 over 4 minus 2 square roots of 2 over 4 is a negative square root of 2 over 4. Let's simplify that, right? So dividing by a fraction is the same as multiplying by the reciprocal. Square root of 2 over 4 times negative 4 over the square root of 2. And boy, doesn't that reduce pretty darn nicely. That's a negative 1. So that's the slope of the tangent line. Slope of the normal line would just be 1. Is the slope of the normal line. After all that reducing, it was just negative 1 and 1. And then we want the equations of the tangent and normal lines. So the tangent line is going to be y minus square root of 2 over 2 equals negative x minus the square root of 2 over 2, or y equals negative x minus the square root of 2 over 2 plus the square root of 2 over 2. That probably simplifies out pretty nicely. If you wanted to write it in slope-intercept form, it would just be y equals negative x. That would be a square root of 2 over 2 plus another square root of 2 over 2. So plus 2 square roots of 2 over 2. And hey, those would cancel. So it just ended up being plus the square root of 2. If you wanted to put it in slope-intercept form. And then the normal line. Same point, just change the slope. Not necessarily the same y-intercept, however, if I write it in slope-intercept form, but the same point. So it would be y minus the square root of 2 over 2 equals x minus the square root of 2 over 2, because it would just be 1. And if I add a square root of 2 to both sides, if I wanted to write it in slope-intercept form, this would just be y equals x. Right? Because negative square root of 2 over 2 plus a square root of 2 over 2, that's just 0. Right? So there we have it, our normal line and our tangent line and the normal line. Not too difficult once we're done. Pretty easy slope. That's just a practice problem that we're going to skip. All right, here's the next one. We just want to find the derivative. Here we have a product, and anything that's already written up there was already in your notes anyway. All right, so we have to use a product rule here. We have we have two products. We have x squared y and we have xy squared. So the first term is x squared, its derivative is 2x. The second term is y, its derivative is dy dx. Right? And then for xy squared, the first term is x, the derivative of x is 1, and the second term is y squared. The derivative of y squared is 2y dy dx. And let's find the derivative. All right, so we've got 2x, just a little power rule there. Oh, excuse me. Sorry, I'm looking at the x squared. It's just an x squared. That's a product. Derivative of the product, x squared y, pays to look at the entire term, is going to be the first, which is x squared, times the derivative of the second, which is dy dx, plus the second, which is y, times the derivative of the first, which is 2x, plus the first, which is x, times the derivative of y squared, which is 2y dy dx, plus the second, which is y squared, times the derivative of the first, which is just 1. So write it down. If you want, we can write a 1 down there. And then equals the derivative of 2x is 2. All right, so let's clean that up, and we'll move the terms with without dy dx to the other side. So we have x squared dy dx plus 2xy dy dx. I like to have the x first and then the y. Equals, everything else is going to move now, 2 minus 2xy. I just change the order there. And then minus, that's just going to be a y squared. Factor out the dy dx. So that's dy dx times x squared plus 2xy equals 2 minus 2xy minus y squared, and then divide everything by x squared plus 2xy. So see, it looks more complicated than it is. Once you get the hang of it, it's actually pretty easy, most of these. And we're done because there's no term there's nothing to reduce. Right? No term has any of the same. There's no factor that's common to all those terms, in other words. So we're done, and we were only asked to find the derivative. Right? And this one is in your notes. This one is not in your notes. You're certainly welcome to write it down, but it's not in your notes. We have a chain rule here with the x plus y. So let's take a look at that. All right. So if we want to take the derivative of that x plus y squared, right? So that we're taking the derivative of blop squared, right? So we would have the derivative of the blop squared Right? And then we need the derivative of the blob. Right? So then we'd have to take the derivative of the x plus y part. Right? So the derivative of blob squared is 2 blob. What's the blob? X plus y. And then we need the derivative of the blob. The derivative of x plus y is going to be, so it's going to be times 1 plus, the derivative of x is 1, the derivative of y is dy dx. Right? So, and then, if you notice, our dy dx is stuck there in a product. You will have to simplify that, but before we do that, let's come over to our derivative. So the derivative of the x plus y squared, we just did off to the side here, little chain rule part, just to review that. So that would be 2 times x plus y times 1 plus dy dx. We got a dy dx stuck there. Derivative of y is dy dx, and the derivative of 2 is 0. We have to simplify that. So we're going to FOIL, right? So don't worry about the 2. X times 1 is x, so the first would be x times 1. The outer terms, x times dy dx is plus x dy dx. Then the inner terms would be plus y, and then the last 2 terms, plus y dy dx, plus dy dx equals 0. Oops, don't forget our parentheses, right? Because the 4 terms there are multiplied by 2. So we'll distribute the 2. 2x plus 2x dy dx plus 2y plus 2y dy dx plus dy dx equals 0. We have more terms with dy dx's than without dy dx's, so we'll move the terms without the dy dx. So that gives us 2x dy dx plus 2y dy dx plus dy dx equals negative 2x. We'll subtract 2x, subtract 2y. Right, so we've got do all the dy dx's on one side, which means now we can factor out dy dx. Right, and we factor out dy dx in the parentheses. We have 2x plus 2y plus, well, dy dx divided by dy dx is 1. Equals negative 2x minus 2y. And then just divide both sides by 2x plus 2y plus 1. To isolate dy dx. So dy dx equals negative 2x minus 2y divided by 2x plus 2y plus 1. And no reducing can we do. Boy, somehow I had used up too much space in the beginning. That didn't give me much space at the end. Let me see if I can move that up. There we go. And we are done with this problem. Right? So it's not, I didn't leave a space for it in your notes, but it is a good problem that maybe you want to have. Right? And there's plenty of space on that cover sheet for implicit differentiation. By the way, this is the last one that's in your book right now. And those are some practice problems that you might do in class. This one's in your notes, right? So this is kind of similar where we're going to need to do a chain rule. And as a reminder, when you've got a function within a function, you take the derivative of the outside, and then the inside doesn't change, right? The gx part doesn't change, g of x. And then you take the derivative of the inside, the g prime of x, right? So this part here is the derivative of the outside. This part here is the derivative of the inside. And this is all in your notes already, what's off to the side there. All right, first of all, though, let's change that radical to an exponent. So that would be y plus xy to the 1/2 power equals 2. Right? So on the inside there, we have a product we have xy, right? So the first is x, its derivative is 1. The second is y, its derivative is dy dx, right? So to take the derivative here, we have the derivative of y with respect to x, so that's dy dx. Right? If it were just an x, it'd be 1, but because it's a y, right, it's a dy dx, because we're taking the derivative with respect to x. Plus the derivative of xy to the 1/2, right? So the derivative of blop to the 1/2 is 1/2 blop, and the blop doesn't change. We're using a power rule here, so that's going to reduce by 1, so that's going to be to the negative 1/2 power. And then we have to take the derivative of the blop, and I don't think I left myself enough space, so I'm going to move this over a tad. Move over, move over, move over. There we go. All right, so the derivative of xy would be times the first, which is x, right, times the derivative of the second, which is dy dx, plus the second, which is y, times the derivative of the first. So that's just going to be plus y. Equals 0, because the derivative of a constant is just 0. Okay, and so now we're going to need to, look at dy dx is all trapped in parentheses there, and we've got a negative exponent as well. So we're going to simplify that negative exponent, and we're going to distribute. Well, first we'll distribute, and then we'll deal with the negative exponent. So we have dy dx plus, all right, so we're multiplying the 1/2 xy to the negative 1/2 times the two terms there, because we're going to have to distribute. So if we multiply by the x, we're going to have, right, so the x is not in, by the way, not raised to the power, right? So it's not going to be in the radical there, and I'll leave it, I guess, as an exponent for right now. So we have 1/2 times the x, that's just going to be x divided by 2 times, and actually maybe it makes sense right now to move that underneath. I'll still leave it as an exponent. So that'd be xy to the 1/2, dy dx is in the numerator. All right, so I just multiplied that term times x dy dx, and I got to multiply that term times the y. So that would be y. And the 2 and the xy to the 1/2 is in the denominator. Equals 0. Okay. So now we need to move the term without the dy dx to the other side. So we have dy dx plus this monstrosity here, x dy dx divided by 2xy to the 1/2 equals negative y 2 times xy to the 1/2. All right, and I'm almost thinking I prefer it as a square root. We'll factor out the dy dx. So that's going to be 1 plus x over 2, I guess I'll change it, square roots of xy equals negative y over 2 square roots of xy. All right, so now we're going to have to divide both sides by that, right? The worst part of this problem is just the simplifying, because we've got a complex fraction to deal with. All right, so that's divided by 1 plus x divided by 2x square roots of xy. All right, so continuing on here, oops, and I'm giving you a hint as what to do. Oh, whoops, that's too far. Off to the side there, we're going to multiply the term over itself to eliminate the negative exponent. So I actually simplified the negative exponent because I kind of like that. I like it better this way, I think. But we've got dy dx equals negative y over 2xy all over 1 plus x divided by 2xy, or 2 square roots of xy. So what do you think we're going to multiply everything by? If you said 2 square roots of xy, you're correct. And then it won't be a complex fraction anymore. All right, so you get, oops, did we lose somebody? Yeah, we didn't. You get a 2 square roots of xy, you get a 2 square roots of xy, and you get a 2 square roots of xy, and now it won't be a complex fraction anymore. So what looked like a mess in terms of the simplifying it, I think it's a little nicer if you write it as radicals, and you can see, oh, there's a 2xy in the denominator on some of these terms. I don't want that 2xy in the denominator, and if I multiply every term by that 2xy, I won't have a complex fraction anymore. So in the numerator, we are left with dy dx equals negative y divided by, we've got 2 square roots of xy plus an x. I don't care about radicals in the denominator. We just don't want complex fractions. That's good enough for me. Okay. And the tape is, this video is a little longer than I realized, so I'm going to stop and I'm going to pick up with a couple problems on the next video. Okay. Bye for now.